Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we just started the new topic, that is concept of stress, and there we have seen that how you can define the stress at a point, right. And then basically we are discussing something and regarding the planes, right. So, any plane can be defined by its direction normal and the plane which will be defined as the positive plane. So, that means the direction normal on that particular plane will be directed towards the positive direction of the coordinate axis. Like if I say this is my positive x plane, that means the direction normal on that particular plane is towards the positive x direction, right. So, we defined the positive faces as well. So, now if you come back to this figure basically, so there is a body and this is the body, and the body is under different external forces like F3, F2, F1 and all. And now we are cutting this body in two halves. So, this is the plane, the cutting plane, okay, which is normal to the x axis. So, that means it is the x plane. So, as shown in the figure, so this plane is nothing but your positive x plane as per the figure. Now, on that plane particular, on that plane, if we discretize this different say segments, right, like this is one segment, this is another segment, this is another segment, likewise several segments are there. So, if we discretize that and if we consider one say segment like this, this is the segment which is containing the point O, and on that plane actually on that particular segment your delta F, that is the force, okay, is acting. Okay. It is not necessary, as I told you in the last lecture, that it is not necessary that delta F will be always perpendicular to the plane, right. That means towards the direction normal, it may not be or maybe, right. So, in more general way if you think of, so it is not normal to the plane. Okay. So, now if we take out, okay, if we separate or if we take out this plane and if we show only that particular plane or particular say segment, okay, so which is containing point O. So, this is the this shaded part is that particular segment whatever we are considering. Okay. So, this is the I mean depth of the plane is a delta y and length of the plane is a delta z, and this is the x plane, positive x plane. So, the area of the plane or area of the I mean small segment will be say delta Ax, okay, which will be equal to delta y into delta z. That is very simple, right. Okay. Now, as I told you in the previous figure, what you have seen that delta F, that is the force, is acting on that particular plane on that particular segment, okay, and basically at point O say. And now, if this delta F is decomposed or resolved in three different say components, force components like in x direction, in y direction and in z direction, then I will be getting delta Fx, delta Fy and delta Fz. Now, this delta Fx, delta Fy and delta Fz are the three components of the force, actual force delta F. And now, this delta Fx, delta Fy and delta Fz, these forces are acting towards the respective coordinate direction. Okay. Now, if I want to define, now one thing is very clear from this figure, that the nature of stress developed by the force delta Fx may not be similar to the stress developed by the force delta Fy, right, because their line of action on the plane, okay, the behavior of these forces on the plane will be completely different, right. So, based on that we can define different stress components on that particular plane. So, let us define that. The stress component perpendicular to the face will be called as normal stress. Okay. So, we are defining the stress as normal stress when the stress component is perpendicular to the face. That means, whatever plane we are considering, if the stress component is normal or the perpendicular to that particular plane, then that stress component will be defined now onward will be defined as normal stress. Okay. So, that means, if you have this plane like this and if you have the stress component which is completely normal to this plane, then that stress component will be defined as normal stress. Now, if you come back to this figure, so whatever is shown here, okay, so you have three components of the force, that is delta Fx, delta Fy and delta Fz. Now, this delta Fx, if you look at, so this face is nothing but the positive x face as per our definition, because the direction normal on this plane, on this face basically will be towards the positive x direction, right. So, therefore, this face is nothing but the positive x face. So, once it is positive x face, then this delta Fx will be acting as the normal or perpendicular to the plane, right. So, normal stress will be defined on that particular face like this, sigma xx is equal to, the definition will be remaining same, delta Ax tends to 0, that means the area of that particular segment whatever I have shown you, delta Ax means delta y into delta z, right, delta Fx over delta Ax. So, this is the definition of normal stress. So, this delta Fx is the normal force acting on that particular plane, okay, and delta Ax is the area on which this force is acting. So, when delta Ax tends to 0, then basically that will define the stress, and that stress will be defined or will be called as normal stress, because it is acting normal to the plane. Okay. So, now there is one thing to be noted, it is shown sigma xx. So, sigma will stand for normal stress now onward, whenever we will be talking about sigma, then that will completely denote. Okay. So, I mean we will not be repeating this thing again and again, but whenever we will be writing sigma, so that will denote the normal stress. Okay. Now, after sigma I have written two subscripts x x. Now, what does it mean? So, please try to understand or please try to remember this thing throughout this course. Now, we will be defining the stress, right. So, when you define the stress, basically you need two things. One is that on which plane the stress component is acting and in which direction, right. Unless until you tell or you mention these two things, then the definition of that particular stress is not complete. So, what I mean to say that if you write sigma xx, that means sigma will denote for, as I told you, normal stress, fine. Now, xx means the first subscript will stand for plane on which the stress component is acting, and the second subscript will stand for direction. Okay. So, normal stress generally when we are defining normal stress, so we will be having the both the subscripts are same. Why? Because what is your normal stress? Normal stress is means on that particular plane along the same direction, right. Now, if this is the normal stress which we are defining for that particular x plane. So, that means the on the x plane it is acting and along the x direction. So, x plane on x plane, so this is my if it is my x plane along the x direction, if the stress is acting, then only I will be saying that thing as normal stress. So, on x plane along x direction, that will be defined by sigma xx, that is the normal stress. So, whenever you are having the normal stress, so both the subscripts must be same. Okay. So, please try to understand now onward whenever we will be using this kind of notation. So, that will define the stress components on a particular plane along a particular direction. Now, for our convenience now onward, because as per our discussion that whenever you are defining the normal stress, then both the subscripts will be same. So, therefore, we will be simply writing sigma x or sigma y or sigma z. So, if I write sigma x, that means that is the normal stress on x plane. If I write sigma y, that will be normal stress on y plane, and similarly sigma z. So, we are not going to write now onward, because it is quite understood. So, if I write sigma x, that means both the subscripts are same xx. So, instead of writing twice, now onward we will be writing only sigma x or sigma y or sigma z, that will define the normal stress on the respective planes. Is that clear? Okay. Now, apart from that, so what we have defined here? We have defined the stress based on the force delta Fx. Now, similarly, you have other two force components, one is delta Fy, another one is delta Fz, right. So, if you look at the figure, if you come back to this figure, okay. So, delta Fx was perpendicular to the plane, but delta Fy and delta Fz, these forces are along the plane, right, are parallel to the plane. Okay. They are not normal to the plane, they are parallel to the plane. So, these forces will be defining some different stress components. So, let us define that. So, the stress component parallel to the surface will be called as shear stress. Okay. So, that will be defined by tau. So, whenever we will be writing now onward tau, that will be simply defining the shear stress. Okay. So, tau. So, if I write tau, that will define the shear stress, and then I can write x y limit delta A x tends to 0, delta F y delta x. Okay. So, this is the definition of the one shear stress component. So, you will be having two shear stress components on a particular plane, right. So, if this is your x plane, right, normal to the plane, you are getting normal stress, that is defined by this, and you will be getting one shear stress along the y direction, another shear stress will be occurring or will be acting along the z direction, right. So, when I am writing tau x y, so tau is defining the shear stress, it is denoted, I mean shear stress is denoted by tau as I told you. Now, what is the definition of these two subscripts? The first one will define the plane as I wrote here, right. So, first one will be defining the plane. So, this tau x y when I am writing, the first subscript is x, that means this shear stress is acting on x plane, but in which direction? The second subscript will tell about the direction. So, y is the direction, is that clear? So, whenever your subscripts are not same, right. So, if your subscripts are same x x, then that means normal stress. If your subscripts are not same, then basically that will define the shear stress. You look at there. So, that means this stress component is acting on x plane, but in y direction, and that is defined by this, because which force is causing this kind, or which force is developing this shear stress? Delta F y, right. So, delta F y over delta A x, when delta A x tends to 0, that will give you the shear stress component along y direction on x plane. Okay. Similarly, you will be having another component of shear stress, that is tau x z, okay. So, tau x z means the shear stress acting on x plane along z direction, and that is defined by delta f z over delta A x, because delta f z is causing that shear stress, okay, when delta A x tends to 0. So, what you have got from this say discussion, you have got that on a particular plane. So, along, I mean through the point O, I have drawn one x plane, right. We started with that. Through a point O, we had drawn a line or drawn a plane which is nothing but the positive x plane. Now, on that particular plane you have got 3 stress components, 1 normal stress component and 2 shear stress components, right. Similarly, if you draw a y plane through point O, the same point, and if you draw a z plane through point O, then you will be getting another 3 plus 3 6 components of stress, understood. So, when I am drawing one x plane through point O, I have got 3 stress components. Similarly, I can draw a y plane, okay, through point O, on which you will be getting another 3 stress components, and I can draw another z plane through point O. So, you will be getting 3 more stress components. So, you will be getting total 9 stress components, which will be defining the complete state of stress at that particular point O. Is that clear or not, right? So, let us write down that for our complete discussion. So, we can write, so these are the stresses in x plane. So, whatever stress components I have shown you, like sigma x x, tau x y and tau x z, all are acting on x plane. So, if you consider one x plane on which some force, say delta F is acting, so you can have the components of that delta F along x direction, y direction and z direction, and based on that you can define the stress component. So, you will be getting 3 stress components. So, these are the stresses are acting on x plane, right. So, now similarly there will be three stress components in y and z planes, right. So, therefore, on x plane you have 3 stress components, on y plane you have got 3 more, and on z plane another 3 stress components will be coming. So, at point O, okay, you can define the state of stress with 9 stress components. Okay. So, let us write down those stress components. So, sigma xx, tau xy, tau xz, sigma tau yx, sigma yy, tau yz, and finally tau zx, tau zy, and sigma zz. Okay. So, this is your in the matrix form. So, this is your complete state of stress at point O. So, whenever somebody is asking you what is the state of stress at that particular point, you have to find out all 9 components. Okay. So, out of these 9 components, 3 are normal stresses, which is quite obvious, and other 6 components are the shear stress components. Now, there is some speciality of this matrix. If you look at this matrix, along the row, if you look at along the row, basically it is defining the plane. The first row is defining x plane, the second row is defining the y plane, and the third row is defining the z plane, right. So, if you take the components of the first row, then basically you are defining the stress components on x plane. Similarly, the second row will define the stress components on y plane, and likewise the third row will define the stress components on z plane. Now, if you look at the column wise, what you are getting here, column wise you see these one normal stress and 2 shear stress components. So, they are defining the stress components along x direction. The first column will define the stress components along x direction. It could be on different plane. So, it is not necessary that on x plane only x direction force will be there or the stress will be there, right. So, on y plane you can have x direction stress, that will be nothing but your shear stress. So, you are getting along column 1, basically you are getting the stress components which are acting along x direction. Similarly, the second column will give you the stress components are acting along y direction, and likewise the third column will give you the stress components which are acting along the z direction. Now, one more thing you need to remember or you need to see here, that is worth noting, along the diagonal, okay, this diagonal of the matrix is giving you the normal stress components. Okay. The diagonal of the matrix will give you the normal stress components. Okay. So, now with this discussion, if we define the x axis as one axis, y axis as 2 axis, and z axis as 3 axis. Okay. So, 1, 2, 3 axis system if we define, then basically that will give me the stress components like this. So, if we define x, y, z as 1, 2, 3 axis system, then basically the on plane 1, that means actually on plane x, the stresses are acting sigma 1 1 limit delta A1, that is the area of plane 1 tends to 0 delta F1 delta A1. So, that is the definition of the normal stress on plane 1. What is plane 1? Basically, we are just mapping. I mean, this is the initiation of your initial notations, though that is not included in your syllabus, but I just give you some indication or some kind of hints by which you can think of the initial notations later on when you will be going through the advanced level mechanics course. Anyway, so what we are doing here, we are just mapping x, y, z to 1, 2, 3 coordinate system, okay, and then we are defining sigma 1 1 by this. Delta A1 is nothing but the area of plane 1, okay, and delta F1 is the force acting towards one direction, okay. Similarly, I can write now instead of tau, I am writing sigma. There is no problem, because in the initial notation, when you will be writing your computer code or when you will be going through the advanced level mechanics course, you will see that everywhere it is defined as sigma. Stress is defined as sigma. Now, if the subscripts are same, then that is normal stress. If the subscripts are different, then that is shear stress, okay. So, here your subscripts are different. Now, sigma 1 2, what does it mean? Okay, what does it mean? That means that this is the shear stress on one plane along two direction, okay. So, that is defined by limit on the same area tends to 0 delta F2 delta A1. Similarly, sigma 1 3, that is the shear stress acting on one plane act towards third direction, 3 direction, okay, that is given by limit delta A1 tends to 0 delta F3 by delta A1. Agreed? So, these are the stress components, one normal stress and two shear stresses, right. So, these are the stress components acting on plane 1. Similarly, you can define other stress components, there are 3 stress components on plane 2 and plane 3, right. So, what we can write, all components of stress can be written as, so all component of stress can be written as in the initial notation sigma ij is equal to limit delta ai equal to tends to 0 delta Fj delta Ai, where I and j take the value 1, 2, 3. Okay. So, now if you look at this, so this is the basically initiation of your initial notation kind of thing. Okay. So, that is very much there in your advanced level mechanics. However, we are not, I just wanted to say this thing at this stage so that you will understand the genesis of your initial notation. However, we are not going to discuss this thing further in this particular course. So, sigma ij is your stress components. If I is equal to j, then basically that will be giving you the normal stress. If I is not equal to j, then that will give you the shear stress, okay, as per our discussion. And then the sigma ij, the stress components, is given by this equation, whatever we have derived from this. okay, where I and j will take the value of 1, 2, 3, fine. Okay. So, now if you look at the stress components acting on different planes, so if I consider one point O, okay, so this is my point O, this is my point O, and around point O if I consider a parallelepiped, I am drawing one parallelepiped in the xyz coordinate system, and then we can find out these are the stresses acting on each plane. So, how many planes are there? 2 x planes, 2 y planes, 2 z planes. 2 x plane means one positive x plane, one negative x plane, right. Similarly, one positive y, negative y, and one positive z and negative z plane, right. So, there are 6 planes. So, on these 6 planes, so this is the point O, right. So, we are taking we are drawing the parallelepiped around point O. So, what is this plane? This plane is nothing but your negative x plane. So, on that negative x plane, these are the stresses are acting, sigma x, tau xy and tau xz, right. Similarly, if I consider this is my negative y plane, right, this plane is my negative y plane. So, on that plane you are having sigma y, tau yx and tau yz, and likewise all the stress components are acting on the respective planes. Now, you may ask me what is this sigma y prime. So, on this plane, on this negative x plane you have sigma x, tau xy and tau xz, but on the positive x plane you have sigma x prime, tau xy prime and tau xz prime, right, because they will be different. Why they will be different? Because you are moving from this point to this point, this much of distance you are moving. So, there will be some variation of stress. So, that I will be coming later on, okay, when we will be talking about the equilibrium condition and all. So, basically due to this variation you are getting the difference in the stress components, but their definition will be remaining same, okay, one normal stress and 2 shear stress components. Okay. So, I will stop here today. So, in the next lecture we will be talking about the plane stress condition, that is nothing but the special kind of stress, state of stress than the special kind of state of stress when we are talking about the 2 dimensional state of stress. So, that we will be discussing, because this whatever we have discussed so far, this whatever is discussed here. So, basically that will give you the 3 dimensional state of stress, right, when you have all 3 coordinate axes or all 3 the stresses are acting in all 3 directions. So, at that time whatever stress components you are getting, so that is defined by this matrix, but will be restricting most of the mechanics problem, at least in this particular course we will be dealing with the 2 dimensional state of stress, and there we will be getting either plane stress or plane strain. When we will be talking about the strain, at that time it will be coming as plane strain. So, however, in the next lecture we will be talking about the plane stress condition, which will be coming out as a special case from this general condition, general state of stress. Okay. So, I will stop here today. Thank you very much.